let's talk about dot products and what dot products are used for. So it's finally time for us to do U dot V. Usually when you look in a textbook, they're going to make this dot extra big. They're not going to do like just a little like kind of dot. They're going to do like a significantly larger dot to try to remind you that dot product is a different process than just multiplying. Okay. So the way we calculate a dot product is we do U1 times V1, and we add to it U2 times V2. So we multiply the components and add them together. So some examples of a dot product. Let's say that U terminates at 3, 4, and V terminates at 2, negative 3, and we're going to do U dot V. So I multiply the first components, 3 times 2, and then I add to it the product of the second component, so 4 times negative 3. So that gives me 6 and negative 12, so negative 6 is my dot product. All right, so let's say U terminates at 2, 2, and V terminates at 1, negative 1. I want you guys to find that dot product. And U is 0, 4, and V is 3, negative 2. Calculate that dot product. So that'll give you a couple to try. I need to ask a question. It's a fairly simple calculation, I think. It's just a matter of remembering what to do. Okay. Much like we did at the beginning of our vectors unit, let's talk about some properties. But now these properties will have to do with the dot product. All right, some properties. U dot V is always going to be the same thing as V dot U. Because all that would do is flip-flop these two things, right? Which would mean you would get the same result. Notice that when we calculate the dot product, is our result a vector or a scalar? Our result is a scalar when we calculate a dot product. Okay, some other properties. If I dot the 0 vector with another vector, what am I going to get? 0 every time. Okay, if I've got a U and I dot it with the sum of 2 vectors, what do you think would be a legal move there? So you can dot it with each one of them individually. U dot V plus U dot W. Okay, what if I have a constant C that I'm multiplying times a dot product? This is the same thing as multiplying the U times the C and then dotting the result with V. Or dotting the U with the c times v. So you can multiply that c by either one of your vectors before you do your dot product, or you can do your dot product first and then use your scalar. But notice you can only use it once. You can't distribute it to the u and the v. You'll get the wrong answer. Does that make sense? So don't use c twice or you'll wind up in the wrong place. Okay, and then one more thought here. What happens if I dot a vector with itself? How would I do that calculation? What'd you say? No, it's not doubling it. Won't you have v1 squared plus v2 squared? And man, that seems really familiar, doesn't it? What do we do with that calculation to find usually? Magnitude. So this is the magnitude squared, right? We would have to square root this to get to magnitude. So when I dot a vector with itself, I get its magnitude squared. All right, so let's do a couple of examples using some of these properties. Number 4, oh, you know what? You need to know what the vectors are. U is going to be 3, 4. V is going to be -2, 6. And W is going to be 1, -1. Let's calculate U dot V times W. Notice that I did my times symbol as an asterisk. That helps me mentally to recognize that dot product and multiplication by a scalar are not the same thing, right? Those are two different processes. And so I use two different symbols for them. So the big dot is dot product. The asterisk is going to be scalar multiplication. Okay, so what I will do here is dot u and v. So I'll do 3 times -2 plus 4 times 6. And then I'll take that result and multiply it times my vector w. -6 plus 24. Sounds like 18 W. So if I take 18 and the vector 1, -1, that result is going to be 18, -18. Okay, let's do one more. Let's do U dot 2W. So this is what we were saying with the C. I can deal with the C anytime I want to. I could double W and then dot product, or I can dot U and W and then multiply the result times 2. I should get the same answer no matter which way I do it. So I'm going to dot first. If you want to do it the other way, do it the other way, double first, just to show you that they are the same. So sometimes when I do these, the result is a vector. Sometimes when I do these, the result is a scalar. It just depends on that particular problem. What's going on with that? Questions on 4 or 5?
Wait, yeah, on 5, like, you did U times...
I did u dot w. That's what's inside the brackets. And then I doubled at the end. But you could just the same, you could double w and then do your dot, and you would get the same answer.
Okay.
So these properties give you a little bit of leeway in how you do your calculations sometimes. Okay, so what do we use a dot product for? Well, the place that a dot product is probably the most helpful is when we're discussing the angle between two vectors. So let's say I have some vector v and some vector u, and I'm trying to describe this angle in between them. The formula is cosine theta is the dot product over the product of the magnitudes. Would you believe me if I said that formula's got something to do with law of cosines? It's got a really similar feel to it as law of cosines, doesn't it? So let's say we've got u at 3, 0 and v terminating at 1, 6, and we want to find the angle between them. So what I'll do is I'll say cosine theta is, and then I'm going to dot my vectors, 3 times 1 plus 0 times 6 over the magnitude of u, which is 3, times the magnitude of v. That might take a little more work. Square root of 37. So I've got 3 over 3 root 37, which is just 1 over root 37. That's not going to be anything on my unit circle, so that's when I reach for my calculator. What am I going to type in my calculator to get the angle? Inverse cosine of 1 over root 37. And if you're in degree mode, your calculator is going to tell you that that is 80.538 degrees. When I get to the end of these problems, sometimes I just don't feel like I have any idea if my answer is reasonable or not. And so if you're feeling that way, it might be a good idea just to make yourself a little sketch. 3, 0 would go this way. 1, 6 would go this way. Is it reasonable that that theta right there would be 80-ish degrees? Yeah, that seems reasonable. If I got 12 degrees, I might be concerned, right? Or if I got 300 degrees, I might be concerned. So that kind of gives me a frame of reference for reasonability. Okay, one new vocabulary word, and we are done. Orthogonal. Orthogonal. Two vectors are orthogonal if they meet at 90 degrees. What word would we use for two line segments that meet at 90 degrees? Perpendicular. So this is the vector form of perpendicular. Orthogonal. The way I test to see if two vectors are orthogonal is by their dot product. U dot V will always equal 0 if they are orthogonal. So when I do the dot product, if I get a 0, I know my two vectors are orthogonal. Look up at example 2. We got a 0, didn't we? So that means these two vectors are orthogonal. And if I sketch them, let's see, 2, 2, 1, negative 1. Well, looky there. That looks pretty close to 90 degrees, doesn't it? So it's fairly easy to convince yourself if you're right or wrong by looking at a sketch. Help you decide if you've done them right or not. How you doing? It looks like so much, right? If you look at the page, you're like, ooh, that's so much. The homework is kind of the same way. When you look at it, you're going to feel like, oh, this is so much. But I promise it's not as bad as it seems. Most of what's on the page is me telling you what vectors to use. So in this first section, all you're going to do is calculate your dot product. In the second section, you're going to calculate these various things using these three vectors. 9, 10, and 11, use your cosine formula to find your angle between the two vectors. 12, 13, 14, test if they're orthogonal, which really just means you need to do your dot product again, right? And then 15, hopefully, is going to make you think a little harder. That's what it's designed to do.